So in section 4.3, we're going to talk about graphing exponential functions. So what we mean by exponential, again, is anything in the form y equals a times b to the x. So the a and b are called parameters. The x and y are the variables. So that just means the a and b may change from one problem to the next, but within the problem they stay fixed, whereas x and y are free to be whatever they can be. So also remember that a is going to be our initial value. That is, when you plug in 0 for x, you're going to get b to the 0 is 1. That's equal to a, and that's also then going to be the y-intercept. And b is what we're calling the growth factor, and it contains within it that information. It's 1 plus r or 1 minus r. So if b is bigger than 1, then it's increasing by whatever r percent is. And if it's less than 1, then the 1 minus r, that b holds the 1 minus r, where the r is the percent. It decreases each year. So we want to have a feel for what these look like. So we're going to graph here in yellow, y equals 3 to the x, in green, y equals 6 to the x, and in blue, y equals 8 to the x on the same axes. So we have an idea for what these look like. So when x is 0, we know that 3 to the 0 is 1. When x is 1, we know that 3 to the first is 3. When x is negative 1, 3 to the negative 1 is 1 over 3, which is 1/3, so about here. Now, as we continue to the right, this thing takes off and gets steeper and steeper. When this thing goes to the left, it's going to get closer and closer to the x-axis. So we will say that y equals 0 is a horizontal asymptote to the left. Now, 6 to the x shares the point 0, 1, because when we put in 0 for x, 6 to the 0 is also 1. But when you plug in 1, it's all the way up now to 6. So as soon as we cross the y-axis, it's going to get much steeper, much faster. On the other hand, when you go to the left, 6 to the negative 1 is 1/6. That's smaller than 1/3, so it's going to hug the x-axis even faster than y equals 3 to the x as we go to the left. In a similar fashion, 8 to the 0 is also 1, so it's going to share that point there. It's going to be 8 when we get to x equals 1, so it will be even steeper still, and it will also hug the x-axis even steeper. So I like to think in my own mind anyway, that when you look at this y equals a b to the x, or if we're choosing here a to be 1, so if we have y equals b to the x, the bigger that b is, then the closer to a right angle this thing approximates. Okay, so let's now take a look then. We're going to go back and look at their reciprocals. 1/3 to the x, 1/6 to the x, 1/8 to the x. Notice down here that you can see that 1/3 to the x is 3 to the negative 1 to the x, which is 3 to the negative x. And likewise, 1/6 to the x is going to be 6 to the negative x, and 1/8 to the x is the same as 8 to the negative x. And you may remember what y equals f of negative x does. It's going to be that reflection in the x-axis. So 1/3 to the 0 is still going to be 1, but now 1/3 to the first is going to be that 1/3, and 1/3 to the negative 1 is going to be 3, and so we're going to get that reflection of the, oops, I kind of missed there. See if I can fix that. So we're going to get that 1/3 to the x is going to be the reflection of 3 to the x in the y-axis. Similarly, our 1/6 to the x, so you get 1, 2, 3, 4, 5, 6. It's going to the left be above 1/3 to the x, and I'm going to have to really squeeze it in there. That's trying to hug the x-axis even faster. And then our 1/8 to the x is going to be steeper still to the right. You're going to have to use your imagination and still trying to squeeze in between there. So that's going to be our reciprocal functions there. Let's look at the next panel. And now we want to figure out more, what is this a doing in this problem? So remember, we said this is the initial value. So 3 to the x, remember when x is 0, it's going to look something like this. So there's our 3 to the x. And then if we include the 2 there, it's going to multiply that each y value by 2, and so it's going to be lie above there. Now, it's not just that it's not translating this thing up 1, it's multiplying every y value by that 2. So these, the red and the yellow, are not the same shape. But in particular, we see that that point that was at 0, 1 moves to 0, 2, but the asymptote does not change. It is still y equals 0. In a similar fashion here, our y equals 5 to the x is going to look something like that. Cross at 0, 1, rise from left to right, and have the x-axis as an asymptote. Now that 0.01 is going to get multiplied by a half, so each y value is going to be half of what it was before. So still we have the y equals 0 asymptote. Now the y-intercept will be 0 a half, and it's going to be a little flatter shape. Our 1/4 to the x, remember, is going to be our decay function. It's going to fall from left to right. And if we multiply by 3, then that point that was at 0, 1 is now going to be at 0, 3. And every y value will get multiplied by 3. So we will have a y-intercept of 0, 3, but still have y equals 0 as a horizontal asymptote. So let's talk more about these horizontal asymptotes. Now, our book starts out using this notation as kind of a warm-up to what the actual formal notation is. So it's going to start by just saying f of x arrow x as x arrow infinity. We're going to go ahead and just start with the actual notation that is going to be used eventually by our book and by other math people everywhere. So we write that as the limit as x approaches infinity of f of x equals k. That's how you read that. And it means that y equals k is going to be a horizontal asymptote. We're going to see that here momentarily. So what we're looking for in the green here, we can see visually what's happening if we think about what the graph of y equals 3 to the x looks like. Remember, it's going to be an exponential growth function. So what we're saying is, as x gets bigger and bigger and bigger, 3 to the 100, 3 to the 1,000, 3 to the million, it's taking off and going up in a huge way. The y values are growing large without bound, so we say that limit is going to be infinity, and we write that infinity symbol. Now, as x goes to negative infinity, as we put in really big negative numbers, 3 to the negative 100, 3 to the negative 1,000, remember that that negative exponent makes it 1 over 3 to the positive exponent. So that's going to be a huge number in the denominator, only 1 in the numerator. 1 over a very large number is going to be very close to 0. And so we will say that that is approaching 0. In a similar fashion, remember, whoops, there's my left hand coming into play again. So remember that 1/2 to the x is going to be this decay function. It's going to fall from left to right. So in this example, when x gets really, really big, when you take 1/2 raised to a really big number, every time you multiply by a half, the value gets smaller. A half times a half is 1/4. A half times a half times a half is 1/8. So as we put in bigger and bigger numbers here, the values of 1/2 to the x get really close to 0. You can see that as you move way out to the right, the curve approaches the x-axis. And then as we approach really big negative numbers, then like 1/2 to a negative 100 would be 1 over 1/2 to 100, or 2 to the 100. It's going to get huge. You can see on the graph as you go way out to the left, the y values get really, really large. We say this is going to go to positive infinity. So our definition of what it means to be a horizontal asymptote involves this limit notation. If the limit as x goes to infinity or the limit as x goes to negative infinity of the function is a finite number, then we say y equals that number is a horizontal asymptote. Let's go on to the next panel. So here we're going to try to solve equations graphically. So we're going to use our graphing calculators here, and we're going to try to graph as y1, we're going to put in this 3 times 2 to the x. As y2, we're going to enter 25, and what we're going to solve then is where is 3 times 2 to the x, where is that going to equal y equals 25? So I'm going to suggest a window, and this is supposed to tell you the x min and x max, and this what to use for the y min and y max. When you do that, you should see a graph something like what we have over here. And what we want to do is find that point of intersection. In particular, we want to find that x value here. So if you, after you've graphed these on the window that I gave you there, if you go seconds, and then the trace button is right up there next to the graph button, go down, you can arrow down to option 5, the intersect option, and then hit enter when it says, is this the first function? Hit enter again when it says, is this the second function? Because it is. And then if you need to, you can use your right and left arrow to move the cursor close to the point of intersection, and then hit enter one more time. And on the bottom of the screen, you'll see the x and the y coordinate. We know the y coordinate is going to be 25 because that's our intersection with y equals 25, but you should get rounded to 3 decimal places, x to be 3.059. Now we're just trying to get these skills on the graphing calculator for now. We'll come back and solve some of these equations using logarithms a little bit later, but for now we're just going to use our calculator. So see if you can try the next one and graph for y1 the x plus 2 and y2 the 2 times 3 to the x. And if it's fine asking you now, be careful how the question is asked. If it's asking for an intersection, then we want the intersection of those two curves should be given as ordered pairs. So to 3 decimal places, you should be able to get those as the points of intersection. And you may need to pause it and do this, but I'm going to go on here. On the next one, it's just asking you to solve this equation for x. So in this case, we're still going to graph y1 as the left side and y2 as the right side and find that intersection. But in this case, there's going to be 2 points of intersection. We're just looking for the x values because we're trying to solve that equation. And you should get those as your 2 x values for those 2 different places where those curves intersect. Another kind of problem is going to be a 200 milligram sample of carbon-14 decays according to this equation, Q of t equals 200 times 0.886 to the t. We want to know when will there be 20 milligrams left. So we can put in y1 as our equation here and y2 as our y2 equals 20. Use our same strategy there, and we want to find that point of intersection, and hopefully you should get 19.024, and that's going to be time for us. And we didn't really have time units here, so I don't know if that's going to be seconds, minutes, days, years, or what. But so we'll just leave it as t equals 19.024. Another skill we want to have is to come up with this exponential regression equation. So remember, we did this earlier with a linear regression, so we're going to do the same kind of strategy that we did before, but we'll just modify it a little bit with our to get an exponential regression. So here's our values, and this is supposed to be representing the population of Houston since 1960. So time 0 is 1960, and time 10 is going to be 1970, and so on. Our P is in thousands, so Houston is a huge city. So at time 0, we have 1,583,000. That means the population of Houston in 1960 was 1,583,000. So we're going to first try to get this equation, so P of T. So on your calculator, you're going to go to Stat, and then hit Enter for Edit. And remember, you may have to go up arrow and to get onto the L1, and then hit Clear and Enter to wipe that clean. And likewise, go over to L2, up arrow into, that's called the formula bar, and hit Clear and Enter to wipe that clean. Then go back to L1 and you can put in 0, 10, 20, 30, 40, 50, right arrow, and you can enter those p-values in there. Once you have done that, you're going to go to Stat again and then right arrow to Calculate. And if you start arrowing down, we'll see 4 is the linear regression, 5 is quadratic, 6 is cubic, 7 is quartic, 8 takes you back to a linear regression, just switching the order of the slope and the y-intercept. 9 is a logarithmic, and finally 10 is your exponential regression. So when you hit Enter, then remember when you arrow down to that 1, 2, 3, fourth line where it says Store Regression Equation, you want to type in Y1. So to do that, remember you go variables, that's that VARS, that is just left of the clear button, and then you'll go right arrow to get to the Y variables, and then you can hit Enter, and you'll see Y1 gets highlighted, hit Enter again, and that will will automatically then store your result into Y1 on your graphing menu, which is going to make your life easier down the road. Then you can down arrow to Calculate and hit Enter, and we'll write it down just rounding to 3 decimal places, but our calculator will automatically store all of the decimal places of accuracy that your calculator can hold into the Y1 list in the graphing menu. So if you did all of this stuff right, we should be getting that our P of T is going to be, here's my left hand getting in the way, 1,685 times 1.026 raised to the T power. So the second question is, what is the percent increase? So remember, our B, our 1.026, holds that information because it's 1 plus R. When you subtract off the ones, that's going to make R equal to 0.026. When you make that into a percent, it's telling us that the population of Houston is increasing by 2.6% per year. Now, part C, this is the part that a lot of us did not do well on the last test. It's saying, what does the model predict will be the population of Houston in 2017? Since time 0 is 1960, 27 will be 57 years later. Now remember, you don't want to use your rounded values that you have here. You want to type in Y1 of 57 onto your calculator. It will then use all the decimal places of accuracy that it transferred over to Y1, and when you do that, I believe you'll get it's going to be 7,437,000 is going to be the population of Houston in 2017. All right, on the next panel, one more little thing here. So can we graph an exponential function whose limit as you go to infinity is 4, and as you go to negative infinity is -2? So, these are two different questions. Hold on there. So if we go to infinity on the first one, so I'm going to do the first one in yellow. So if our limit as x goes to infinity is 4, that means that it's going to approach 4 going to the right. So if we are going to have an exponential and it's got to approach 4, it's going to have to be a decay curve, something like that. And on the green one, if as we go to the left, it's going to approach -2, that means we need a horizontal asymptote to the left at y equals -2. And so that means it's getting smaller to the left. It must be some kind of exponential growth function there. All right, very good.